Welcome students, welcome to the next session of strength of metals 1. So in the previous class we have completed our derivation for calculating shear stress at a section in the beam. Now we are going into different stress variation diagrams, how the shear stress is varying from point to point along the depth. Okay, for that I am taking different types of beam sections. Firstly, I am considering rectangular, circular, I section and T section. So considering these different sections, how we have calculated our section modulus, like that here also I am taking different beam sections, and along the depth of the beam, what is the shape of the stress distribution diagram for the shear stress. Okay, firstly, our first example is rectangular beam. So for that I am considering a rectangular beam with width B and depth D. So I am considering a rectangular section of a beam with B width and D depth. So we have imagining a width of a B and a depth of D, and in that let F be the shearing force acting at the section. So shear force at the section they have given in the condition. Now consider a level EF which is at a distance y from the neutral axis. Firstly, before giving the indication of EF, I should have to indicate neutral axis. So the neutral axis is at the centroidal distance, centroidal axis of the section, as it is being the symmetrical, the neutral axis, centroidal axis and geometrical center are being coincided. That's why total depth divided by 2 will be the location of neutral axis, and this neutral axis is at d by 2 from top and d by 2 from bottom. And now after giving the indication of the neutral axis, we are giving the indication for the EF level. So I am considering a level EF which is at a distance y from the neutral axis. Okay, so this is my condition. Why I have considered like that portion? As you already remember the formula tau, shear stress at a point or at a level, tau is equal to FA y bar by I into B. So that A is indicated as area of the portion above that where you are calculating the shear stress. As I am calculating the shear stress at the level EF, I need to involve this area above the level EF. Okay, so this is the condition I am having. Now when you see the picture, you may observe like this, as initial width of the beam as B, depth of the beam as a D, and I am having the neutral axis line which is located at a depth D by 2, and I have indicated a level EF which is at a distance y from the neutral axis, and the remaining height of the section above the level EF is D by 2 minus y, that is D by 2 minus y. So in this way we have completed the initial picture, giving the corners A, B, C, D and indicating the neutral axis and indicating the EF levels. Now I need to calculate shear stress equation at any level, so that I can give the equation and at different points I can calculate the shear stress answer. Now shear stress at the level EF is given by tau is equal to FA y bar by I into B. So FA y bar divided by I into B is indicated as tau. So this tau is equal to FA y bar by I into B. Firstly, this capital F is shearing force acting at the section where I am calculating the shear stress. Okay, so along the beam at some section the shear force is F, and at some point I am calculating the shear stress. Okay, the shear force capital F they have given, and capital A is indicated as area of the portion above we are calculating the shear stress. So as I am calculating the shear stress at the level EF, I need to consider area of the cross section of the beam above the level EF. Okay, area of the section above the level Y, that is shaded portion ABEF or ABFE. See here, ABFE is the shaded portion I should have to consider. Now the area of the particular portion is, as we have already got, the remaining portion as D by 2 minus Y. This one is D by 2 and this portion we left as Y. So this remaining portion is D by 2 minus Y, and this is multiplied with the width of the beam, that one is B. So this portion's height d by 2 minus y and width b. So d by 2 minus y into b is a value. And the next ring is y bar. Y bar means distance of centroid of the shaded portion from the neutral axis. Okay, y bar means distance of the centroid of the shaded portion from the neutral axis. So distance of center of gravity of the area A from the neutral axis. As I am having the section like this and the neutral axis like this, and its distances are like this. This one as d by 2, and I am having the distance of level as y, and this leftover distance is d by 2 minus y. Right? Now, this height, there is an area like this. Okay, in this area, what is happening? There is a center of gravity location. From the center of gravity location, I should have to calculate y bar. Okay. Now, how the y bar will come? As we know, the depth of the rectangle in the center, you will calculate, and the remaining measurement plus y measurement. So, half of this rectangle height, half of the shaded portion rectangle height plus y measurement. So, half of the y measurement plus half of the shaded portion rectangular height. So, rectangular height divided by 2. That one plus y is distance of the center of gravity of the shaded area from the neutral axis level. So, half of d by 2 plus y. So, in this way, d by 4 and minus y by 2 plus y. In this way, after making it common, y plus d by 4 minus y by 2, we have got d by 4 plus y by 2, which as 1 by 2 into d by 2 plus y. Okay, so with the three terms rearrangement, I have got the final term as half of d by 2 plus y. And the next term in the equation is f a over y bar over and then I. I is moment of inertia of the whole section about the neutral axis, nothing but the centroidal axis. I is moment of inertia of the whole section, as it is being a rectangular section with the dimensions b and d, and about the centroidal axis or about the neutral axis, when we are calculating the moment of inertia, that is BDQ by 12, and B is actual width of the beam. In our case, the width of the beam at the level EF is also equal to, at the level EF, what is the width of the beam? That is also B only. Okay, so the same B I should have to continue. Now, substituting all the terms in the equation, tau is equal to F A y bar by I into B. F as it is I'm keeping. A we have got as from the shaded portions area, width and depth. So, B d by 2 minus y into B. And y bar is from the centroid of the shaded portion to the neutral axis distance. This one is d by 2 minus y as it is, y as it is wholly d by 2, and it one with b, and I am having the centroid like this, and which is at this remaining measurement of y and this remaining measurement of d by 2 minus y and half. Okay, so in this way we have got y bar distance, area, I and B. So F initially area, so d by 2 minus y into B as area. So that one is area's answer into what is the remaining thing? Y bar. Y bar means y plus half of d by 2 minus y. Later we have got half of d by 2 plus y as y bar's answer. So half of d by 2 plus y as the y bar's answer, and then I is moment of inertia of the section and B is B only. Now I am keeping I as this, later I will substitute, and we have got it as A minus B into A plus B like that. Okay, F by 2I into D square by 4 minus y square as tau equation for the rectangular section. Whatever is the level you consider, okay, whatever is the level you consider, when it is at a distance y from the neutral axis, the corresponding tau answer is this one. If it is at this level, okay, even though it is below, even though it is above, whatever is the way, okay, but if it is at a distance of y from the neutral axis, either in the top or in the bottom, if it is at a distance of y from the neutral axis, if it is at a distance of y from the neutral axis, I am not considering that is above, that is below. Just at a distance of y from the neutral axis. So I can go up or I can go down. Whatever it is, the shear stress at the section tau is equal to F by 2i d square by 4 minus y square. Okay. Now what it is saying? It is indicating shear stress at any point with respect to the y substitution. Y means distance of the layer from the neutral axis. With respect to y substitution, you will get different answers of shear stress at that point. If it is at the neutral axis, the corresponding y. If it is at some other point, that corresponding y's answer, shear stress. If it is some other extreme fiber, that corresponding y answer and calculation of shear stress. In this way, we will calculate shear stress at different points now. Now, from the equation, what you can observe, that is tau is getting increased with respect to, tau is decreasing with respect to increase in y. See here, when y is equal to 1, okay, 1 square, so something minus 1, okay, that portion's multiplication is coming out. If y is some 2 square, okay, y is becoming 2, so 2 square, so the same quantity minus 4 and the multiplication is stopped. If y is becoming more and more and more, as the y is becoming more, it is taking more portion out, okay. So as y is with negative sign, it is taking more portion out. So as y increases, tau answer is getting decreased, and also tau is in second degree relation with y square. All the remaining are constant. Shear force at the section, moment of inertia of the section, depth of the beam, and all these things are being constant. Only the thing is second degree equation for the shear stress, as the y and tau are having the second degree relation. The variation of the shear stress with respect to y will be parabolic. Okay, tau is in a relation with a parabolic equation. So from the equation, tau is increasing. Tau increases as the y decreases. Or in the reverse condition also you can write tau decreases as the y is increasing, because y increasing means negative portion increasing. So overall multiplication will be reduced. So tau will be reduced. And also the variation of tau with respect to y is a parabolic, because just now only we have some with respect to y, it is having a second degree equation for tau's answer. Y increases with respect to second degree equation, tau answer will be coming. Okay. Now at the top edge, what is the top edge position? When I am taking the neutral axis, this top edge is at d by 2. When it is measured from neutral axis, the corresponding y is d by 2. At the top edge, y is equal to d by 2. Substituting that, I have got the shear stress d square by 4 minus d square by 4 is equal to 0. We have got the shear stress at the top edge is equal to 0. Okay, shear stress at the top edge is equal to 0. Similarly, when you go down further rectangle, here also y is equal to d by 2 only. Symmetrical section, geometrical line, everything is there with the coinciding with the neutral axis. So, again, in the bottom also, this bottom edge also, the shear stress is equal to 0. Okay. So, at the top edge and bottom edge it is 0. Any other special point? Yes. At the neutral axis I will try to calculate. Okay. At the neutral axis means the neutral axis is located, and from the neutral axis, measurement I will call it as y. Distance of any layer from the neutral axis. Distance of extreme layer from the neutral axis. Distance of extreme layer from the neutral axis is y. Now, I am calculating shear stress at the neutral axis. So, distance of neutral axis from the neutral axis, that y is equal to 0, because at the axis itself I am calculating. That's why y is equal to 0, and with the substitution in the equation, f by 2 into d square by 4 is the answer, and f d square by 8i is the shear stress when I am calculating the shear stress at the neutral axis. And f d square by 8i. Just now only we have said I will substitute later whenever it is needed. Okay, now the moment of inertia I is equal to bd cube by 12, as it is being the rectangle and the neutral axis is its own centroidal axis. That's why f d square by 8 bd cube by 12. So, substitution of f as it is, d square as it is, 8 as it is, only this I is equal to bd cube by 12. So, the shear stress tau at the neutral axis, okay, at neutral axis tau is equal to, cancelling all the terms, I have got 1.5 f by bd. Okay, so what is this f? F is the shearing force at the section. So, how much shearing force it is having on the plane? Okay, some shear force will come, right, if it is the beam section. that shear force answer F, they have given as the shear force F, and by BD. Now, when you write the average, see the whole structure indication and then average shear stress. So, what do you mean by the average shear stress? Generally, when you have any shear force and that shear force is acting on an area, what is the formula for shear stress? Shear stress is equal to shearing force by shearing area. Okay, shear force by shear area. If that is coming like this, shear force by shear area on which the shear is traveling, okay, on which the shear is acting. Okay, if the body is having like this and it is having the shearing force like this and this is the area. So, F by area is the shearing force by shearing area, that is shear stress. If the same thing is happening like this and the body is having some shear force like this. Okay. Now, the shearing force by shearing area is the answer for the shear stress. Generally, shear stress means average shear stress only. Okay. On an average, what is the shear stress in rough value? Okay. That average shear stress F by this shearing area. When this is our cross section of the beam and I have observed a rectangle with B and D. Okay, on which only the shear stress is acting. That's why F by BD. The tau average is equal to shearing force by shearing area. Now, shear stress at the neutral axis is equal to 1.5 times F by BD only now. So, that is tau average. In the previous step only I have got tau at the neutral axis is equal to 1.5 F by BD. But now I have got tau average is equal to F by BD. So, the shear stress at the neutral axis is equal to 1.5 times the tau average. Shear stress at the neutral axis where y is equal to 0 is the maximum value. Yes, as y decreases, tau increases, right? As the y is decreasing, tau is increasing. As y is becoming the least possibility. Least means y can go 0 only. That least it is reaching. So, tau is becoming its highest. As the y is becoming least, the tau will become highest. So, the tau maximum will be occurring at the neutral axis. The tau maximum is equal to 1.5 times F by BD. But F by BD is tau average only. That's why tau max is equal to 1.5 tau average. Okay. In this way, we will calculate a relation between maximum shear stress in a rectangular section. Sorry, with the average shear stress in the section. Now, when you represent in a picture, what you can see? See here, I am having a rectangular section and being the neutral axis aligned, and at the neutral axis, the tau is equal to F by 2i F by BD 1.5. And at this top edge, tau is equal to 0. At this bottom edge, tau is equal to 0. So, 0, 1.5 F by BD 0. And indicating the variation as the same height as the depth of the beam. Okay, same height as depth of the beam and indicating the neutral axis. At top edge 0, at bottom edge 0, and at here the neutral axis level, that one is tau maximum, and I have got this value as 1.5 F by BD. And connecting all these 3 points, okay, positive side only, positive x like that I have given, okay. On the positive side every value I have got, and connecting all these points, the equation is a parabolic. In the previous step we have given the relation between tau and y is parabolic, right? So, as I am moving along the depth, the corresponding tau answer will give a parabolic form. So, with a smooth curve, I am connecting all these things. So, with that smooth curve, the neutral axis should be at the center, maybe the rough value I have not given at the center. In this way, for the rectangle section with the same depth, I am indicating the picture. Now see the variation, indicating as it is a depth, as it is a height, and indicating the neutral axis line. At some other point, I have got a cube with some other height as y. Okay. With respect to tau answer, and it is tau max. Okay. So the tau max, tau and y. For every y, there is a tau, and at the neutral axis, the tau is tau maximum. At the edge, it is 0. Okay. Now I am going into a problem for a rectangular section. So just now we have completed shear stress variation in a rectangular beam. I am taking an example. A rectangular beam 100 mm wide and 250 mm deep is being subjected to a maximum shearing force of the shear force acting on the section, we have got it as 50 kilonewtons. And what they are asking us to determine, we should have to determine the average shear stress, we should have to determine the maximum shear stress, and also the shear stress at a distance of 25 mm above the neutral axis. As it is a rectangular section, firstly I should have to indicate the neutral axis level. Okay, I am indicating the neutral axis. Where the neutral axis will be located for the symmetrical sections, as it is being a symmetrical section, the neutral axis will be at half the total depth, okay, which is at 125 mm from top, 125 mm from bottom. In this way, we have got the neutral axis location as N and A. Firstly, what I should have to calculate? They are asking us to determine the average shear stress. Average shear stress means simply the shearing force, how much the shearing force is acting, divided by what is the shearing area, okay, on which the cross section the shearing force is applying. That area is my shearing area. So I have given the given data, width of the beam as 100 mm and depth as 250 mm. So width 100 mm and depth 250 mm, and the shear force they have given, the applied shear force as 50 kilonewtons, and it is 50 kilonewtons. And we have mentioned all the things, like only we should have to substitute in newtons and mm. So I am taking 50 into 10 cube newtons. Okay. Now average shear stress is equal to 50 into 10 cube newtons average shear stress shearing force by shearing area, which is 100 into 250 mm. Okay. In this way, Newton per mm square, the corresponding answer will come. Shearing force by shearing area on which the force is acting. Average shear stress means simply what the shear stress in the first chapters we have remembered. Okay, average shear stress, but it was generally the shear stress answer. Now, maximum shear stress for the rectangular section. How I will calculate the maximum shear stress? Either we can calculate the shear stress will be maximum at the neutral axis, so that I can calculate shear stress at the neutral axis, or using the average shear stress also I can get it, but I should have to remember the formula. The maximum shear stress will be at the neutral axis, or from the average shear stress I can write maximum shear stress is equal to 1.5 times average shearing stress. So after knowing the value of average shear stress, with the multiplication of 1.5 you can calculate, or otherwise you can calculate measuring the shear stress at the neutral axis. The both are same. So maximum shear stress, either in this condition you can go, or shear stress at neutral axis you can calculate. Both are same because the maximum shear stress is at the neutral axis level only. Okay. The next condition they are asking us to calculate what is the shear stress at the level 25 mm from the neutral axis. So simply we are having a rectangular beam with 100 mm width and 250 mm depth. And firstly we are locating the neutral axis, which is being located at a distance of 125 mm, and our level where I need to calculate the shear stress is at 25 mm from the neutral axis. So from the neutral axis I am indicating the level which is at 25 mm. Okay. At the level I need to calculate the shear stress. So above the portion I need to consider the area. Okay. without remembering the formula, by using the basic concept and analyzing for area, F, I, Y bar, everything also you can solve. Okay, in that way I am calculating. Otherwise, if you remember, you can use the formula we have got. Okay, that F A Y bar by I into B, where capital F is equal to shearing force at the section. That one is, how much shearing force they have given? 50 kilonewtons. That's why 50 into 10 cube we have written there. When we are substituting, you can write that. So, the shearing force acting on the section is 50 kilonewtons. And then, capital A is area of the beam above the level 25. Yes, above the level 25, what is the rectangular area left that I should have to consider? A width of 100 mm and a depth of, how much the depth I left? 125 total and removing the 25. So, 100 by 100 is the area of the rectangle in the shaded portion. 100 by 100 mm square. And then Y bar. What is the meaning of Y bar? Y bar is indicating distance of center of gravity of this shaded portion from the neutral axis. So this is my Y bar, distance of center of gravity of the rectangular shaded portion. What I am considering from the center of gravity line to the neutral axis. Okay, how I will calculate? As I know this 25 as it is. So 25 plus this shaded portion's half height. Being a rectangular, the center of gravity is at half the level. So, remaining 50 plus this remaining 25. 50 plus 25 is the depth. Now, the total of 100 depth of the shaded portion by 2 plus 25. So, in this way, the 75 mm depth as the Y bar we have got. And capital I is moment of inertia of the whole section. Being it as 100 by 250. So, B will be 100 and depth will be 250. BD cube by 12. In this way, we will calculate moment of inertia of the whole section. Only here, I only will be considered for the whole section. A will be above the shaded portion. Y bar will be from the shaded portion to the neutral axis. And then capital B, actual width of the beam section at the level where I am calculating the shearing stress at the level EF. When I am calculating the shear stress, being it as a symmetrical section, the width EF is as it is equal to the width of the rectangle. So, the width of the rectangle is 100 mm only. So, as we have already calculated, A, Y bar, I and B. And in the problem they have given F. So, F, A, Y bar by I into B, we will substitute now. So, substituting all these answers, F 50 into 10 cube newtons we have got. And area of the shaded portion, 100 by 100 right, we got right. So, 100 by 100 is my area. And if you want, you can write the units only for the reference, no need to indicate here. And Y bar is distance of center of gravity from the neutral axis. That one is 75 mm. And I is moment of inertia of the rectangular section, width B and depth D by 12 into what is the width of the beam? Always that is 100 only. So, with these units, this is in mm per 4. With the analysis, finally, we have got the value of the shear stress at the level 25 with the units 2.88 Newton per mm square. So, we have calculated the average shear stress. What do you mean by average shear stress? In general, what is the shear stress? We know shearing force by shearing area that we have calculated. And then maximum shearing stress in the rectangular section. We have got a relation tau max is equal to 1.5 times tau average. So, using this condition, we have calculated the next answer. And then we have calculated shear stress at a level. Further, from the basic principles I went there without using the formula. Okay. In the next class, we are going into the next section, which is the circular section for the shear stress distribution diagram. Thank you.